Hi students, welcome to our physics online class. In the previous class, already you learnt about Cartesian sign convention. It is very important topic while we are dealing with the spherical mirrors, right? Okay, now I am going to start next to new topic, mirror equation from the chapter ray optics. Chapter ray optics, the topic name is mirror equation. Mirror equation, right? First, what is mirror equation? Then what is its use, right? First, what is mirror equation? Very simple. The relation connecting object distance, image distance and focal length of a given spherical mirror is known as a mirror equation, right? The relation connecting object distance, image distance and focal length of a spherical mirror is known as mirror equation, right? What is object distance? The distance between the pole of a spherical mirror and the object is known as object distance, right? What is image distance? The distance between image and pole of a spherical mirror is known as image distance, right? What is focal length? The distance between principal focus and pole of a spherical mirror is known as focal length. The relation which connecting these three is known as a mirror equation. Mirror equation, right? What is its use? Suppose if the distance of the object from the pole of a spherical mirror value is known and focal length of a given spherical mirror value also known. From these two values, we can find out what is the distance of the image formed by the spherical mirror from its pole. Right. Suppose if the object distance and the image distance values are known, from that two value, we can find out what is its focal length. Similarly, if you know object distance and if you know the image distance and focal length of a spherical mirror, we can find out the object distance, right? So it is a use of mirror equation. Mirror equation means the relation connecting object distance, image distance and focal length of a spherical mirror is known as mirror equation, right? Okay, it is necessary to derive mirror equation in order to determine the unknown value. That is, it may be object distance or it may be image distance or it may be focal length, right? From a simple ray diagram, we can derive mirror equation. Okay, so a simple ray diagram is required to derive mirror equation, right? Are you clear what is meant by mirror equation and what is its use? Mirror equation means the relation connecting object distance, image distance and focal length. Already you know about object distance, image distance and focal length. The distance between pole and the object is known as object distance. The distance between pole and the image is known as image distance. The distance between pole and principal focus of a spherical mirror is known as focal length. The relation which is connecting these three is known as mirror equation. What is its use? If you know any two value, okay, other value can be determined by using mirror equation. To derive mirror equation, a simple ray diagram is required, right? This is a simple ray diagram to derive a mirror equation, right? So first let I explain about ray diagram. So this is concave mirror, which is called a concave mirror. A mirror whose reflecting surface is curved inwards is known as concave mirror. Okay, so this is reflecting surface. The reflecting surface is curved inwards. So that is what is called concave mirror, right? And this is a pole of a concave mirror. What is meant by pole? The center point of the reflecting surface of a given spherical mirror is known as a pole. The given mirror is concave mirror. Okay, the corresponding pole is P. Okay, the pole of a given concave mirror is represented by P, right? Next, what is F? F be the principal focus of a concave mirror. Principal focus of a concave mirror. Already you know about what is meant by principal focus of a concave mirror and convex mirror, right? Okay, next, what is the C? C be the center of curvature of a given concave mirror. Center of curvature of a given concave mirror. What is meant by center of curvature? The center of the reflecting surface of a given, or the center of curvature means the center point of a given spherical surface is known as center of curvature. Center of curvature. Next, C. What is C? C be the center of curvature of a concave mirror. Center of curvature of a concave mirror. What is center of curvature? Center of curvature is the center of the sphere of which a mirror forms a part. Center of curvature be the center of the sphere of which a mirror forms a part. Okay, C be the center of curvature, F principal focus, and P pole of a given concave mirror. Concave mirror, right? And what is AB? AB be the given object. Okay, AB is the object. Right. This object is placed on the principal axis of a concave mirror. Principal axis of a concave mirror. What is principal axis? An imaginary line or a line which is passing through center of curvature and the pole of a spherical mirror is known as a principal axis. Okay, so this line is passing through center of curvature and the pole of a given spherical mirror. So that is why it is called principal axis. Principal axis. Here the object AB is placed on the principal axis. Okay, placed on the principal axis. Right, where? Okay, far away from the center of curvature of a concave mirror. Right? An object AB is placed on the principal axis far away or behind the center of curvature. Behind the center of curvature. Right? Okay. Now we consider three paraxial rays from the point B on the object AB. Right? AB be the object. From the point B on the object, we consider three paraxial rays. Paraxial rays. What are called paraxial rays? Simple. Already you learnt in the previous class. That is, the rays which are traveling close to the principal axis. The rays which are traveling close to the principal axis and instant on a given spherical mirror close to the pole. Close to the pole. And makes small angle with the principal axis is known as paraxial rays. Okay? The rays which are traveling close to the principal axis and instant on a given spherical mirror close to the pole. Close to the pole and makes small angle with the principal axis is known as paraxial rays. Paraxial rays. For our convenience, we consider three paraxial rays from the object, where from the point B on the object. Right. So one of the paraxial ray is BD. Okay. This paraxial ray BD is parallel to the principal axis. So this is principal axis. Okay. One of the paraxial ray from the object from the point B, okay, is a BD, which is parallel to the principal axis. Parallel to the principal axis. Right. Okay. This paraxial ray is instant on this concave mirror at point D. At point D. After the reflection, it travels along DB dash direction. Right? So BD be the one of the paraxial ray which is considered from the point B on the object AB, which is parallel to the principal axis and instant on the point D, instant on the concave mirror at the point D. After the reflection, it travels along DB dash direction. DB dash direction, right? And second paraxial ray, BP. Okay, BP, right? So this paraxial ray is travel towards the pole of a concave mirror. Okay, second paraxial ray is travel towards the pole of a concave mirror. And instant at point P, after the reflection, it travels along PB dash direction. PB dash direction. Right? So this is the second paraxial ray which is travel towards pole. After reflection, it travels along PB dash direction. Right. And the third paraxial ray is BE. Third one is B, which is travels through center of curvature. Okay, third paraxial ray is BE, which is travels through the center of curvature and strikes on the concave mirror at point E. At point E. We know the rule. If any ray which is travel towards or travels through the center of curvature for a given spherical mirror, and strike on the given spherical mirror, after the reflection it retraces its original path, or it after reflection it travels along the same path. This paraxial ray is travels through center of curvature. After reflection from the concave mirror, it travels along the same direction. Same direction, right? So there are three paraxial rays should be considered from the object in order to derive mirror equation, right? So what are the paraxial rays? One is BD, second BP, and third BE. First paraxial ray is parallel to the principal axis, and after reflection it travels along DB dash direction. Second paraxial ray is BP, which is strikes or which is travels through or towards the pole of a concave mirror and strikes at point P. After reflection it travels B dash direction. And third paraxial ray is travels through center of curvature and strikes on the concave mirror at point E. After reflection it retraces its original path. Right? So these three paraxial rays are incident paraxial rays. Right? These three are reflected rays. Okay, which are a reflected ray? One is DB dash, second PB dash, and third EB dash. These three are reflected rays. Right? These three reflected rays intersect at point B dash. Right? At point where two or more than two reflected rays intersect to each other, the image will be formed. Right? So this is a position of the image. The position of the image or the image is, the position of the image can be drawn by using a perpendicular which is drawn from the principal axis. Right here, A dash B dash be the image. Okay, which is drawn by using a simple perpendicular drawn from the principal axis. Right here, AB be the object and A dash B dash be the image. Where the image will be formed? Okay, at a given point, if two or more than two reflected rays are intersect to each other, there will be image formation. Right here, this is a position of the image. It is represented by A dash B dash. Right. So three paraxial rays is incident on a given concave mirror at point D, P, and E. After reflection, okay, they are intersect at point B dash, where the image will be formed. It is represented by A dash B dash. Right. Okay. So in this ray diagram, in this ray diagram, we consider one of the paraxial ray, that is BP. Okay. So this is incident paraxial ray. This is reflected ray. We consider BP incident ray and PB dash reflected ray. Okay. For these two ray, for this incident ray and reflected ray, according to laws of reflection, this is angle of incidence and this is the angle of reflection. Okay. For the incident ray BP and the reflected ray PB dash, according to laws of reflection, this is angle of incidence and this is angle of reflection. Okay, we know that what is the laws of reflection? The angle of incidence is equal to angle of reflection. The angle of incidence equal to angle of reflection. According to laws of reflection, angle of incidence is equal to angle of reflection. Okay, for our convenience, we consider only this incident ray and this reflected ray. Okay, for this incident ray and reflected ray, this is angle of incidence, this is angle of reflection. According to laws of reflection, angle of incidence is equal to angle of reflection. Here, angle of incidence is BPA. Angle BPA be the angle of incidence for this paraxial ray, right? Which is equal to angle B dash P A dash. B dash P A dash. B dash P A dash be the angle of reflection. B P A be the angle of incidence. According to laws of reflection, angle of incidence is equal to angle of reflection. Right. Now we consider two right angle triangles in this ray diagram. Right. One of the right angle triangle is B P A. B P A. So one of the triangle, right angle triangle B P A. Right. And another right angle triangle B dash P A dash. Right. So in this diagram we consider two right angle triangle. One is B P A. B P A. And second right angle triangle B dash P A dash. Right. Here this is angle of incidence and this is angle of reflection. According to laws of reflection, angle of incidence is equal to angle of reflection. Right. So in this triangle, angle I and in this triangle, angle R, these two are equal. These two are equal. Right. And this is 90 degree in this right angle triangle and this is 90 degree in the triangle BPE. Right. So here two angles are equal in this two right angle triangle. Okay, if two angles are equal in the two right angle triangle, other angle definitely equal. So this angle also equal. This angle also equal. So these two angles are similar triangles. Sorry, these two triangles are similar triangle. Similar triangle. Why they are called similar triangle? Because two angles are equal. If two angles are equal in a two right angle triangle, definitely other angle should be equal. So these two triangles are similar. Two triangles are similar. Right? We know that if two triangles are similar means then their sides are proportional. Their sides are proportional. Okay? From the rule of similar triangle, we know that if two triangles are similar, then their sides are proportional. Their sides are proportional. Right. Here we consider two right angle triangle. One is B P A and another right angle triangle is B dash P A dash. P A dash. These two triangles are similar. Similar. Right? From the rule of similar triangles, okay, the sides in the two right angle triangles are proportional, right? Okay, so from the rule of similar triangle, the side A dash B dash in the right angle triangle B dash P is proportional to the side AB in the right angle triangle BPE. Okay, so B dash or A dash B dash divided by AB should be equal to P A dash divided by PE. P A dash divided by PE. Right? So if two right angle triangles are similar means then then their sides are proportional. Okay, this is a rule of a similar triangle. Right? So here these two right angle triangles are similar. Therefore, from the rule of a similar triangle, A dash B dash divided by AB is equal to P A dash divided by P. P A dash divided by P. So this is taken as equation number 1. Equation number 1. Right. And similarly, we consider another two right angle triangle. One is DPF. 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 And another right angle triangle B dash A dash F or A dash F B. B dash A dash F B dash. Right? Okay, first two right angle triangles are okay BPA and another one is B dash P A dash. And another two right angle triangles also there in this ray diagram. One is DPF and another one is A dash F B dash. A dash F B dash. Right. Here these two right angle triangles also similar because these two angles are alternate angles. Right. Okay. Here these two are two right angle triangle. These two right angle triangles are similar. Why? Because these two angles are corresponding angles. The corresponding angles are equal, and this is 90 degree for this right angle triangle, and this is 90 degree for this right angle triangle. Right? Two angles are equal in these two right angle triangle. Definitely, other angles should be same. So these two triangles are similar triangle. Similar triangle. Okay, we know that if two right angle triangles are similar, then their sides are proportional. From the rule of a similar triangle, okay, A dash B dash divided by DP. A dash B dash divided by DP equal to A dash F divided by PF. A dash F divided by PF. From the rule of a similar triangle, that is triangle DPF and triangle A dash F B dash, the side A dash B dash divided by DP is equal to the side A dash F in this right angle divided by PF in this right angle triangle. So A dash B dash divided by DP is equal to A dash F divided by PF. Suppose this is taken as equation number 2. Right. Here the side DP in this right angle triangle DPF is equal to the side AB in the right angle triangle BPA. Right? So these two sides are equal. That is DP is equal to A. From this ray diagram, the DP side DP is equal to the side AB. So DP is equal to AB. Substitute DP is equal to AB in equation number 2. Right, substitute dP is equal to AB in equation number 2. Then this equation number 2 becomes A dash B dash divided by AB is equal to, because instead of dP we can write AB. So A dash B dash divided by AB is equal to A dash F divided by PF. So this is equation number 3, right? From equation number 1 and 3, comparing equation number 1 and 3, we can get P A dash divided by PA is equal to A dash F divided by PF, right? From the equation 1 and 3, P A dash divided by PA is equal to A dash F divided by PF, because left hand side in these two equations are same. A dash B dash divided by AB, here also A dash B dash divided by AB. So left hand side equal means then right hand side in these two equations are same. So P A dash divided by PA is equal to A dash F divided by PF. So this is equation number 4. So P A dash divided by PA is equal to A dash F divided by PF, right? So in this ray diagram, the side AF can be written as, A dash F can be written as A dash P or P A dash minus PF, right? Here A dash F value is equal to P A dash minus PF. By subtracting P A dash value, subtracting PF value from A dash value, we can get A dash F. So A dash F is equal to P A dash minus PF, right? Subtracting PF value from P A dash value, we can get A dash F. So A dash F is equal to P A dash minus P F. Minus P F. So substitute A dash F is equal to P A dash minus P F in equation number 4. In equation number 4. Then equation number 4 becomes P A dash divided by P A is equal to, instead of A dash F, we can write P A dash minus P F divided by P F. Divided by P F. Right. So let it be equation number 5. Equation number 5. Right. Okay. Here, listen the ray diagram. The distance between pole and the principal focus of a given spherical mirror is called focal length. The focal length is denoted by the letter small f. The distance between pole and the principal focus of a given spherical mirror is called focal length. Right. Here, PF be the focal length of a given, concave mirror. Right. And this is image and this is pole. The distance between image and the pole is called image distance. Image distance. Here image distance is PA dash. Generally the image distance is represented by V. Okay. PA dash is equal to V, because this is image and this is pole. The distance between pole and the image is called image distance. The image distance is denoted by the letter V. Right. And this is object and this is pole of this concave mirror. The distance between pole and the object is called object distance. So PA is equal to U. The focal length of a concave mirror or given spherical mirror is represented by small f, and image distance is represented by V, and object distance is represented by U. Right. By applying Cartesian sign convention, here the object and the image, these two are lies left side of the pole. Left side of the pole. Right. From the Cartesian sign convention, all the distances measured to the left of the pole or left of the origin should be taken as a negative. Right. So image distance and object distance values are negative. And focal length of a spherical mirror value also negative, because the focal length should be measured from the pole to principal focus. This distance also measured to the left of the origin, that is pole. So this value also taken as a negative. Right. So focal length value, image distance value, object distance value should be negative by using Cartesian sign convention. Right. Here PF is equal to minus F, PA dash is equal to minus V, and PA is equal to minus U. Understand? Right. Substitute PF value, PA dash value and PA value in equation number 5. Right. Okay, equation number 5 becomes PA dash is equal to minus V divided by PA is equal to minus U equal to PA dash is equal to minus V minus PF is equal to minus F, small f, divided by PF is equal to minus F, right. Here minus get cancelled. So V divided by U is equal to minus V, minus into minus plus, so plus F divided by minus F, right. V divided by U is equal to, okay, in both the numerator and the denominator is multiplied with the negative sign. Okay, then the numerator becomes V minus F and the denominator becomes F. Right? By multiplying negative sign in both the numerator and the denominator, this term becomes V minus F divided by F. Right? Okay, or V divided by U is equal to V minus F divided by F, or V divided by U is equal to V divided by F minus 1. V divided by F minus 1. Right. V divided by U is equal to V divided by F minus 1. That is, this equation can also be written as V divided by U is equal to V by F minus 1. Right. For our convenience, just to divide the image distance, that is V, in in both sides of the equation in denominator, in denominator, right? Then this term becomes V divided by V into U is equal to, this term becomes V divided by V into F minus 1 divided by V. Okay, divide V in both sides of the equation in a denominator. So this term becomes V divided by V into U is equal to, this term becomes V divided by V into F minus 1 divided by V. V cancel, V cancel. So 1 divided by U is equal to 1 divided by F minus 1 divided by V, or 1 divided by V plus 1 divided by U is equal to 1 divided by F. Right, so this equation is called mirror equation. Mirror equation, right. Already I told what is meant by mirror equation. The relation connecting image distance, object distance and focal length of a spherical mirror is known as mirror equation. Here V be the image distance, U be the object distance and F be the focal length of a given spherical mirror. The relation connecting these three is known as a mirror equation. The mirror equation is 1 divided by V plus 1 divided by U is equal to 1 divided by F. This equation is applicable for all type of spherical mirror. We know that there are two types of spherical mirror, concave mirror and convex mirror. This equation is derived by using concave mirror. Instead of a concave mirror, if you use a convex mirror, the same equation, we can get the same equation, that is 1 divided by V plus 1 divided by U is equal to 1 divided by F, right? So mirror equation is 1 divided by V plus 1 divided by U is equal to 1 by F. What is mirror equation? The relation connecting object distance, image distance and focal length is known as mirror equation. What is the use of a mirror equation? If you know any two value in this equation, another value can be calculated by using this equation. That is by using mirror equation. If you know V value and F value, U value can be calculated. If you know F value and U value, V value can be calculated. If you know V value and U value, from these two values we can calculate what is the focal length of a given spherical mirror. So use of mirror equation is to determine the unknown value. Unknown value means it may be image distance or object distance or focal length. The relation connecting object distance, image distance and focal length is known as mirror equation. So far we discussed about mirror equation, right? Next we will see about lateral magnification. Lateral magnification, right? If any object is placed in front of a spherical mirror, the spherical mirror may be produced magnified image or diminished image or same size as that of an object, right? Okay, a given spherical mirror, how many times a given spherical mirror, spherical mirror magnified the given object that can be determined by using the term called lateral magnification. Lateral magnification, right? Lateral magnification is also called transverse magnification. Transverse magnification, lateral magnification or transverse magnification. Okay, transverse magnification is used to find how many times a spherical mirror magnified the given object, right? What is meant by lateral magnification? Lateral magnification is generally represented by the letter small m. Magnification is denoted by the letter small m, right? And it is defined as the ratio of height of the image to the height of the object. Height of the object. Lateral magnification is also called transverse magnification. It is defined as the ratio of height of the image to the height of the object, right? Height of the image is represented by the letter h prime and height of the object is represented by h. H prime, height of the image, h, height of the object. The ratio of height of the image to the height of the object is known as lateral magnification or transverse magnification. Transverse magnification, right? Here height of the image and height of the object is always perpendicular to the principal axis, right? From the same ray diagram, this is object and this is image. This is the height of the object and this is the height of the image. Both height of the object and the height of the image is perpendicular to the principal axis. Right here, AB be the height of the object, A dash B dash be the height of the image. A dash B dash, that is H prime, and height of the object, that is AB, which is equal to H. Right? Okay, we know that in this ray diagram, the triangle BPA and the triangle B dash PA dash, these two are similar triangle. If two triangles are similar, then their sides are proportional. Okay, already we discussed about that. Okay, here these two right angle triangles are similar. Therefore, from the rule of similar triangle, A dash B dash divided by AB, A dash B dash in this right angle triangle is equal to the side AB in the triangle BPA. So A dash B dash divided by AB is equal to another side PA dash in the right angle triangle B dash PA dash and PA in the right angle triangle BPA. These two ratio also, these two sides also proportional. That is PA dash divided by P. Right? We know the rule of similar triangle. If two right angle triangles are similar, their sides are proportional. So by applying the rule of similar triangle, A dash B dash divided by AB is equal to PA dash divided by PA. Right? Okay. And A dash B dash is equal to H prime. And AB is equal to H. Right? Here PA dash be the image distance, because A dash B dash be the image. This is pole. The distance between pole and the image is called image distance. So PA dash is equal to V. Image distance is represented by the letter V. And next PA be the object distance, because this is object, this is pole. The distance between pole and the object is known as object distance. Object distance is represented by U. So PA is equal to U. Okay, now what we want to do, applying Cartesian sign convention. By applying Cartesian sign convention, all the distances measured perpendicular to the principal axis and above should be taken as a positive. And all the distances measured perpendicular to the principal axis and below should be taken as negative. Here, object distance should be positive and image distance definitely negative, right? From the Cartesian sign convention, right? And object distance and image distance also negative, because all the distances measured to the left of the origin should be taken as a negative. Here image distance and object distance are measured from the left of the origin. So their value is also negative. Right? By applying sign convention, H prime is negative and H value is positive and image distance value negative and object distance value also negative after applying Cartesian sign convention. Okay, after applying Cartesian sign convention, H prime minus H prime. H becomes plus H, V becomes minus V, and U becomes minus U. Right? Substitute A dash B dash is equal to minus H prime, AB is equal to plus H, B PA dash is equal to minus V, and PA is equal to minus U in this equation. Okay, now apply A dash B dash is equal to minus H prime, AB divided by AB. AB is equal to plus H equal to PA dash. PA dash is equal to minus V divided by PA is equal to minus U. Right. Here minus cancel. Okay, minus h prime divided by h is equal to v divided by u, or h prime divided by h is equal to minus v divided by u. Minus v divided by u. Already h prime divided by h is equal to m. So magnification of lateral magnification or a transverse magnification of a given spherical mirror is given by m is equal to h prime divided by h. If you know height of the image and height of the object, we can calculate what is the lateral magnification of a given spherical mirror. Or the lateral magnification can also be calculated by measuring the image distance and the object distance. Okay, it is given by the relation m is equal to minus v divided by u. Okay, m is equal to minus v divided by u. Right. And we know that mirror equation is 1 divided by v plus 1 divided by u is equal to 1 divided by f. 1 divided by f. Right. Or 1 divided by v is equal to 1 by f minus 1 divided by u. 1 divided by v is equal to cross multiply u minus f is equal to divided by uf. 1 divided by f minus 1 divided by u is equal to u minus f divided by uf. Right. Or v is equal to uf divided by u minus f. Okay, taking reciprocal on both sides, 1 by v becomes v and u minus f divided by uf becomes uf divided by u minus f. Substitute v is equal to uf divided by u minus f here. Okay, then magnification equation becomes m is equal to minus, instead of v, uf divided by u minus f divided by u. Right, u cancel. So therefore m is equal to minus f divided by u minus f. Right. Both the numerator and the denominator is multiplied with the negative sign. Then this equation becomes m is equal to f divided by f minus u. M is equal to f divided by f minus u. If you know the focal length of the given spherical mirror and the object distance, we can calculate the lateral magnification produced by a given spherical mirror by using the relation m is equal to f divided by f minus u. F minus u. Right. From the same condition, that is 1 divided by v is equal to 1 divided by f minus 1 divided by u. 1 divided by u is equal to 1 by f minus 1 divided by v. Therefore, 1 divided by u is equal to cross multiply v minus f divided by vf. Taking reciprocal on both sides, u is equal to vf divided by v minus f. U is equal to vf divided by v minus f. Substitute u is equal to vf divided by v minus f here or in this equation. Then this equation becomes m is equal to minus v divided by, instead of u, vf divided by v minus f. V minus f goes to numerator. So minus v into v minus f divided by vf. V cancel. Right. Okay, and minus of v minus f becomes minus v plus f divided by f, or otherwise f minus v divided by f. So this is also one of the equation for lateral magnification. So we have four equation for lateral magnification. They are m is equal to h prime divided by h, second minus v divided by u, and third f divided by f minus u, and fourth f minus v divided by f. The given values are height of the image and height of the object. We can calculate the lateral magnification produced by a spherical mirror by using this relation. If we know image distance and object distance, we can use m is equal to minus v divided by u in order to find the lateral magnification or transverse magnification of a given spherical mirror. Or if we know focal length and image distance, we can use this condition. If you know focal length and image distance, we can, we can also calculate the lateral magnification of a given spherical mirror by using the relation m is equal to f divided by v divided by f, right? Okay, once again, I recall from the beginning. First, what is mirror equation? Mirror equation is nothing but the relation connecting image distance, object distance and focal length of a given spherical mirror. What is its use? To find the unknown value. Unknown value means image distance or object distance or focal length. But we should know any of the two value. Any of the two from the three value. Right. And next, lateral magnification or transverse magnification. Lateral magnification or transverse magnification is defined as the ratio of height of the image to the height of the object. Height of the image to the height of the object. This term gives how many times a spherical mirror magnify the size of the object. The size of the size of the image with respect to size of the object. With respect to size of the object. The magnification of a spherical mirror can be calculated by using some relations. They are m is equal to h prime divided by h, m is equal to minus v divided by u, m is equal to f divided by f minus u, and m is equal to f minus v divided by f. Right? So these are expression for lateral magnification or transverse magnification. Right? Thank you, students.